applied mathematics seminar. Today, our speakers are Hilary and John Ockendon from Oxford University. I do not think the long introduction is needed. Hello, Frank. And so that presentation is recorded. However, because of technical issues, the slides will be presented by our speakers. However, their camera could not work at all. This is why we could not see them, how they are showing something by fingers. However, at the end, when we finish the presentation, when the presentation finished, so we switch off the slides, and you can speak to our speakers and ask our speakers all questions needed. So the presentation is starting. So the Hilary, start your presentation. By the way, all other speakers, all other sources, all other participants, please switch off your microphones and cameras. Then the connection hopefully will be a little. All right, so we are starting presentation, and I'm also switch off my camera and my microphone.
Okay, thank you.
Yep.
Can everybody
start?
Thank you very much, Sasha, for this invitation. All things considered, I'm quite pleased not to have you having to look at my face for the next 45 minutes, and much better to concentrate on the mathematics. Of course, that would not apply if Hilary was giving the talk. So, the story I have to tell you began maybe 10 years ago. Yes, can we go to the first slide, Sasha, please?
No, I'm doing it.
Oh, you've done it. When Tom Mullin, who probably a lot of you will know, is a very famous fluid dynamicist and experimentalist, he was working in Bristol, and he was very interested in how solid objects could slide down slopes when there is a lubricating layer on the slope. And he had the very good idea of instead of watching something slide down a mountainside, to actually make the mountain move and try to hold the solid object stationary. So he produced this configuration in A here, where you have a belt, just a rubber belt, which is flexible, and an oil bath at the base. And the belt goes up at the right and carries a thin film of oil with it over the top, back down, and repeats. And as you can see, he put a circular cylinder near the top of the belt, and he adjusted the speed of the belt depending on the weight of the cylinder that he put on. And a close-up, looking at it, you can see that well, you can't see the film on the belt very well, but I hope you can see two menisci near the top and the bottom, where the film makes contact with the cylinder. The cylinder goes round, but if the belt is going at the correct speed, the cylinder stays stationary as far as its center of gravity is concerned. And what was very dramatic in all the experiments that Tom did, the surface tension of this oil was so small that the capillary number was very large. And in almost everything I'm going to be saying, we won't consider surface tension effects, except right near the end. Anyway, Tom collaborated with Jens Eggers and Rich Kurzweil on this, as you can see, and they wrote a paper which was a lubrication model for that film between the cylinder and the belt. And they made a rather crude assumption that the vertical extent of the lubricating region was governed by the thickness of the film coming in. If you see on the left-hand picture, the film comes in at a certain thickness, and it's at that point where the lubrication starts. And I think that was a first guess, but that's not a very good assumption. So now go to the next slide, please. Thank you. Tom came to Oxford then to work, and he told us about this and asked if we could do any better. And we said, well, we don't much like this circular cylinder. We'd much rather do it with a cuboidal block with right-angled corners, because that way you would know more or less where the lubrication region would be. It would be between the two vertices of the cube. And Tom thought this was a good idea, and we talked about it with several other people. Some people thought it was a very bad idea because it would be much more difficult to analyze because of the corners. I remember John Inch was totally against it, but we prevailed, and Tom made some nice cuboidal objects to be levitated. And the next. So looking from the side for a cuboid, we anticipated this kind of geometry. There would be a Reynolds equation, a lubrication equation, all the way between the block and the belt. And there would be Reynolds equation would hold in that region. And we just put that the pressure was atmospheric, taken to be 0 at each end of the block. And you have three, if you're for a given mass, you want to know what the belt. Obviously, the crucial question for Tom is the belt velocity that supports it. But in doing that, you have to find the thickness of the layer at, let's say, the bottom right-hand corner, and also, of course, the inclination of the block, because the block can rotate a little bit. But you have three equations of motion for the block, and you have three unknowns. It turns out that these equations are very easy to solve, especially for the size of block. Tom was considering gravity was not at all important in the lubrication region. It becomes important lower down on the belt. And when you think about it, then if you neglect gravity in the Reynolds equation, the pressure, the only way that the block cannot rotate is to have near zero shear on it, and so the pressure isn't the dominant force on the block. You don't want to have some sort of torque exerted on this block. So it's quite unlike a normal lubrication flow. Normally with lubrication, the pressure increases like 1 over the gap thickness squared, and you have strong pressures normal to the film. Here you don't have any pressure normal to the film, and it's only the shear force in the Reynolds equation that supports the block. And when you do that, you find the block has to be parallel, obviously parallel to the belt, and the small pressure variations combine with the viscous forces to give you zero torque. And the key result from the practical point of view, yes, is the next slide, is that the velocity of the belt is the square root of the flux times the mass of the cylinder, and the separation of the belt is Q over M. So you can see that the velocity is proportional to the mass. And in principle, for any given mass of block, you use that formula to find the velocity, and if you have the belt going at that velocity, and only at that velocity, will the belt stay stationary and be levitated. However, there was a further twist to the experiment, because when Tom did these blocks, and he did these experiments in Oxford, looking at it sideways on now, so you're looking at the top of the block, he found it could still stay stationary as long as the fluid flow was unsteady. And that unsteadiness took the form of this finger. You can see this finger of fluid, which is slowly growing downwards from the block. And if we had a movie of this, you'd see it would grow longer and longer and eventually go down and hit the bath at the bottom. So there was a spectrum of belt velocities that could lead to a stationary block, but only one in which the fluid flow was steady. So that all worked very nicely, and we wrote a paper on that, and we were very pleased. And then Tom said, well, now we better go back and explain the circular cylinder. So it's exactly the same picture. I've just replaced the block by a circular cylinder, same scraper. But now let's do, so looking sideways on, it's very schematic, the picture at the bottom. And downwards is to the left. You can see one of the main differences that the circular cylinder can, and that indeed does, transport a layer of oil around its whole circumference, and it comes back to join the incoming flow at the left-hand end. So there is a new variable we didn't have for the block. And also, we've got to know not only the thickness of that film around the block, but also we've got to find the angular velocity, omega, of the block. The variables here are tildes because they were just dimensional variables. I'm going to non-dimensionalize them in a minute. Now, what about the conditions for Reynolds equation? Well, we can certainly do the same as Kurzweil and Eggers and Tom, and say that the pressure should be naught at these two turnover points, which I've labeled x plus and x minus. But these are now unknown variables, x plus and x minus. They are two further new variables to be added to the problem. So whereas we had 3 variables for the block, we've now actually got 7 variables to determine for the cylinder. Of course, the P equals naught conditions can be applied to Reynolds equation, but we have got free boundary problem for both x minus and x plus. So I am 2 equations short if I use my 3 equations of motion for the cylinder and the P equals naught conditions at x plus and x minus. So we have an underdetermined problem at the moment. Let's see what we're going to do about that. Well, we're going to do an asymptotic analysis, needless to say, as we've been doing all the time, calling epsilon the thickness of the film compared to the radius of the block, which is now 1. And just ordinary lubrication theories then suggests there's this lubrication region, which is a thickness, transverse thickness epsilon, and its length, it's in the x direction, is epsilon to the half. So you satisfy Reynolds equation. We expect the film around the cylinder to also be of order epsilon. But all the problems are going to arise near this region 2 and 4, the upstream coalescence and the downstream separation of this film. And this is a configuration I'm sure many of you will have looked at before in different contexts. And the number 1 suspect, as always in these problems, is the separation one, region 4. And so we're going to start off by thinking about that in a bit more detail, see if we can find some more information apart from the condition that the pressure is going to be almost atmospheric there. So next slide, please. So we do the typical Reynolds scaling, and there you see, because we're having a curved cylinder, the pressure, the Reynolds pressure, is this large quantity epsilon to the minus 3/2. And again, as in the block, the gravity term is relatively small, epsilon to the 3/2m, where m is the non-dimensional cylinder mass, and that isn't important to lowest order, but it may come back later. So we go ahead. I'm not going to bore you with writing down Reynolds equation. It's a nice linear second order equation for the pressure. And there is the solution in terms of U, the belt velocity, omega, the cylinder velocity, which we don't know, either of those. Q is the flux, U times the initial belt thickness, and H0, which is the thickness at the nip at x equals 0. So there is one constant of integration P0, because I haven't yet imposed the boundary conditions at x plus and x minus. And just to give you a feel for the kinds of pressure distributions we're getting, next slide please, the pressure is always an odd function of x, but it can be shifted by this P0. So if we wanted the pressure to be 0 at finite points x plus and x minus, we could have the symmetric situation in the top picture, where the pressure is actually 0 at the nip and 0 at x plus and x minus. But we could also have x plus and x minus getting quite large, as in the middle picture, or if we make P0 too large, we don't get to any 0 of the pressure except at the origin. So so we're going to start off by thinking of the first picture, where we have two symmetric points. X plus will now be equal to minus x minus. Yes, let's see. And so P is P minus P0 is this odd function. And we have these two, the torque balance on the right and the moment balance on the left, and the levitation force balance on the right. But the cylinder is held up by the pressure now. That integral of xp it's not just the shear force, it's the pressure force which dominates the levitation process. Now, to get to this, to resolve the ambiguity, let us now start looking at region 4. I did that too early. So region 4, just as a lead-in, this question of film separation occurs in all kinds of lubrication problems, in bearing problems, in all kinds of coating flows. And one that's particularly relevant to what I'm talking about was, well, first of all, the history. Reynolds equation started lubrication theory. He realized that when you did lubrication, you got cavitation in the film between the bearing and the surrounding collar or whatever it is. And he realized you had to have a second condition there. And he proposed that not only was the pressure 0, but also that the pressure gradient was 0. Now, I never quite understood what was going through his mind, but it turns out to be not a bad, give quite reasonable results. But then he didn't know about matched expansions and things, and people like Bretherton and Taylor looked at this in the 60s. Bretherton was doing a flow in a parallel-sided channel. Taylor was trying to build in surface tension effects, and so they all proposed very different kinds of second boundary conditions. And the one that was most popular when I was a student was Coyne and Elrod, when I was a postdoc, I guess, who proposed a linear relationship between the pressure and the pressure gradient. And a lot of work was done by Savage and co-workers in Leeds. And then in the middle of the 80s, when computers had developed quite a lot and matched expansions, Coyle, McCosco and Scriven, who were looking at this nice problem of film coating, where you have a bath of oil and you want to coat two counter-rotating cylinders. They were equal and opposite cylinders, so they had the great advantage of symmetry in the problem. And they studied that region near the top where the flow is separating using both numerical and asymptotic analysis. And I'll come back to what they got a little bit later on. I should also say that, you see, it's going to be a two-dimensional region, this separation region. The flow is fully two-dimensional Stokes flow. And Stan Richardson in '68 started to develop a mathematical theory for stress-free boundaries in Stokes flow, which I might come back to that as well later on. Right, now is the time to look at region 4. Now I'm sorry, this is the main slide, and I'm sorry it's handwritten, but we couldn't do any better. And I will go through it rather as slowly as I can. I hope it makes some sort of sense to you. So we're in region 4. To lowest order, the cylinder is parallel to the belt, so we need only consider a parallel incoming flow, incoming from the Reynolds region on the left, where there's a shear flow coming in, so that the stream function, which is going to satisfy the biharmonic equation, is just a cubic polynomial in y, describing those incoming 3 arrows. And at the cylinder top, we have the stream function is constant, and that the horizontal velocity is omega. And at the bottom, again, the stream function is a different constant. The difference between the two is q, the flux we're talking about, and the different velocity u. And now all the problems come as this cavitation starts. This is, I must emphasize, is air, oil, cavitation. It's not evaporation, no evaporation or anything like that going on here. So that is air in the gap. And that boundary has got to be a streamline, which I've chosen to be psi equals 0 for simplicity. But then you have these two awkward stress-free tangential stress, normal stress and tangential stress, but both got to be 0 as well. And then far to the right, we're going to have this flow near the cylinder, which is going to eventually end up going round the cylinder in a region of thickness, which I've called HC. 1 minus HC is that thickness of that region, and Y equals HB is the bottom one, and that probably more is going through there than the top, but we'll see about that. So that is the full problem, and I believe that's a well-posed mathematic. Well, no, I'm not sure. I partly believe that this is a well-posed problem for reasons I'll explain. If we wanted to actually do some analysis on this, in fact, that psi is biharmonic means you can write it in terms of two functions, phi and chi, of complex variable z. But then you've got to bring in these stress boundary conditions. But fortunately, as in elasticity, there is a stream function, but there is also a stress function for slow flow. And the two principal normal stresses are d2a dy squared, d2a by dx squared. And it turns, and the pressure is minus a half the Laplacian of this stress function A, which is also a biharmonic function, and it can also be written in terms of phi and chi in the same way we did for the stream function. And the vorticity term is minus the Laplacian of psi, turns out to be the harmonic conjugate, basically, of the pressure. Both the pressure and the vorticity are harmonic functions. And when you write all that down, and it takes a little bit of time, but I hope you can get the general idea, you find that A and dA by dN are 0. I expect that's no great surprise. That gives sigma n and sigma s to be 0. And if I call Z equals Z star, the equation of this air boundary, you find there are two further complex equations which apply on Z is Z star. Quite simple equations. You can even include surface tension without making them much more complicated. So the whole problem can be formulated just in terms of three functions. So, phi and chi, both of a complex variable Z, and Z bar, which is a complex function of a real variable S, the arc length. And when you do the count of the number of unknowns and what you want to determine, you look at what comes in. We can say we know, if we assume we know everything that comes in, we want to now find the two numbers HB and HC. But in fact, we will know HB because that's the thickness of the film going all the way around. But when you put it this way, it's easier to think of. So there we have what I call a classical slow flow free boundary problem, which has received far too little attention from the mathematical community. I do think there's an awful lot that could be said about this using some of the ideas that I mentioned earlier on, especially using conformal mapping. Anyway, let's go to the next slide and not go rushing off to our trusted colleague Radu Cimpanu, who is a most wonderful CFD person. He used to work in Oxford, and we were very sorry when he went to Warwick. But he has a code which seems to me will solve almost any free boundary fluids flow. He put in surface tension into the problem. He put full Navier-Stokes in instead of slow flow for the oil. He put gas dynamics, viscous gas dynamics instead of the air, and he just did it, and he produced some wonderful results. The ones that give you most intuitive feel. These are contours of the x velocity. So blue is very slow and red is very fast, and you can see that whereas when it's coming in, the slowest velocity is near the middle because it's being dragged along the two outsides, and quite a bit goes along around the cylinder at the top, and then quite a lot goes off and goes around the belt and around the back. Right, now suppose we look more at the next slide, please. Numerically, Radu plotted his outputs for HC and HB and found that there was a unique graph relating HC over HB with the ratio of the belt, of the angular velocity of the cylinder and the velocity of the belt, which was, it was very interesting that Coyle and Scriven, the paper I referred to earlier, they got it with the number 0.65 instead of 2/3 from their numerics. So that was pretty good numerics for 1986. And they also, based on an physical argument I didn't quite understand, they saw that 2/3 was a possible value there. But that result, I think, is absolutely clearly established now, and I really am very cross that no applied mathematician yet seems to have derived it from the problem statement that I showed you below. Of course, that's only one of the two pieces of missing information, but it's if anybody has any thoughts about that 2/3 or would like to go into it further, I do hope they'll ask about it afterwards or email me. Radu also found a formula for X plus in terms of M, which is perhaps a little bit surprising. Quite heavy cylinders, X plus stayed fairly constant as you make the cylinder a bit lighter, U gets less, but then as you get to M going to 0, this X plus is going way off, getting larger and larger, and I've got something to say about that in a little while. Next slide, please. Yes, in fact, even without doing Radu's calculations, if you just look at the 5 equations that you can write down for the 7 unknowns, you can, if you juggle around with them, you can see that when U is small and omega is small and Q is small, they do simplify. You can't solve them precisely, but you can see there is a limiting ratio that M over U cannot go above 4 pi over √3. So that would be an upper bound on the speed for a reasonably heavy cylinder. It's a similar sort of result to what we had for the block. But once the cylinder gets lighter and lighter and M gets smaller, we get U going smaller and smaller and M going smaller and smaller in this sort of ratio, then it looks as if something's going to go wrong because X plus is getting large. And so let us see how we might react to that difficulty, that non-uniformity. And the obvious first thing to do is to say, well, suppose the lubrication region in the nip is actually longer than epsilon to the half. In fact, suppose it's long enough that gravity can have an effect to lowest order, which it never did for the block, and it didn't up till now for the cylinder. And the gravity term, as you can see there, it turns out to be epsilon to the 3/2, and then you just start to think, how large does x have to be, and how big is y? Y squared has got to be comparable to x. How do you get those three terms balancing? And since m is proportional to u, you can actually work out, you'll be able to satisfy the equations of motion of the cylinder for small m, with m being order u, if you do these scalings for y. I'm afraid you do it. M is another small parameter now. It's the dimensionless mass. So I've got two independent small parameters at the moment, and y has to be epsilon to the minus 3/4 m to the half. It's still small, and x is longer than it was. That's bigger than that. Got to be bigger than epsilon to the half, and the pressure is quite a bit smaller now. And there is a constraint on the m, that it's going to be small, but it mustn't get down to epsilon to the 3/2, or else we don't think it is possible to do levitation. Anyway, if you do those scalings, you solve this rescaled Reynolds equation, you just get this linear and then an inverse cubic in x bar in these scaled variables. And I'm calling it the flooded region because physically I'm thinking of the lubrication region getting longer and longer, and in particular extending downwards to meet the incoming fluid, but it'd also be going further and further upwards, but it's going to flood in both directions. But it obviously won't want to flood too far going upwards because it's got gravity going against it. Next slide. Now, if we look again at Radu's computations in a little bit more detail, there is the pressure profile when m is getting smaller, as we're getting to this situation where the x plus and x minus are going to infinity. And you can see, well, we got to minus 20 there on that. I'm not quite sure what scale of x that was. Do you remember, Hilary? It's not scaled with m, is it? Anyway, if you look at you can't see it in the pressure curve in the box, it's as I was drawing it. But if you look in more detail around between minus 10 and minus 15, the picture below shows a blow up of what this pressure is actually doing. And the top rather faint grayish line is where the pressure comes in with zero gradient at the point where there's a green star. And then as you lower m, the pressure goes negative and then comes to a zero, which would presumably be the end of the flooded region where the green x is. And then as m gets smaller and smaller, that green x moves further and further. So the extent of this flooded region, if you determine its end by saying that's where the pressure is naught, just goes down and down, makes the Reynolds equation valid over a longer and longer distance. It's also quite interesting. I know that Mo Awali, our collaborator, has done an awful lot of this work, and I believe he's in the audience. I'm delighted to hear, so he can answer. If anybody is particularly interested in this picture, that there's a critical value of m star, which is the 4 over 3 part. I'm not quite sure what that value corresponds to, where it is possible for a branch point that occurs in the algebraic equation you're solving, and x plus and x minus can diverge. So x minus gets on getting larger and larger, negative, the curve going upwards, and x plus can now get smaller and smaller in magnitude and start going down, which is the sign that the flooded region at the top is not having a happy time and it doesn't want to go any longer. So there is a funny kind of bifurcation in this nonlinear problem at a critical value of n. But from the purposes of the actual levitation of the cylinder, it's the top branch that I'm interested in. And you can see that that is still getting larger. It goes on growing without bound. Right, now what does that suggest? This is really the final slide, but I'll take a little while to explain it. So we have a sort of situation where we have this incoming belt film on the far left of this picture, and up to now that has been going as a constant thickness all the way under the cylinder and gone out off the right hand side, well, somewhere near the right hand end of this picture, and met the film that's been coming down around the cylinder. But in line with this flooding phenomenon that I've been talking about, as m is getting smaller and smaller and omega is getting smaller and smaller, u is getting smaller and smaller, this flooded region is encroaching from the right, and suddenly it's going to interact with the region where the film coming around the cylinder meets the film coming up the belt and produce another, well, seriously two-dimensional Stokes flow with a free boundary, which would look like a squashed up version of the picture I've drawn here, where that left-hand bump has moved quite a bit to the right. And then I envisage, as you go even slower and lower velocity and smaller mass, that this the sum of the film coming around the top of the cylinder goes down and forms one of these tongues, such as we saw for the block back on at the beginning of the talk. And such a tongue could grow, I presume. But this is purely, well, it's not completely speculation, because although when Tom did the experiments with the cylinder, he again got a unique velocity for, just as we did when he was doing the original Bristol experiment, he got a unique velocity for a given mass. He said, well, once things get light, these cylinders, he had a sequence of cylinders where it would just annularize, so he could make them lighter and lighter with the same radius. He did see signs of something going on beneath the bottom end of the lubricated region, and I suspect that if he was to do more experiments, we would be able to establish this possibility of a downward going tongue. I think that's more or less all I want to say, except that this picture and several of the earlier ones, we've been talking about free surface slow viscous flows, which have got quite high curvature. Here you can see there is high curvature both near where the cylinder meets the belt and near the tip of the tongue. And of course we had high curvature in the separation region I was talking about earlier. Now, I forgot to say that in Rado's computations, he actually put surface tension in. I think it helped his numerical code. And the numerics, unfortunately, tended to become less and less reliable as the capillary number went up and as the surface tension went down. So it could just be that the zero surface tension limit is a singular limit for this problem, and whether surface tension is important in the picture I've got here or not is also an interesting open question. That's just about all I want to say, except to just end with one recollection and possible word of warning. The picture, could I just go back to the handwritten picture, Hilary? Is that asking too much? Thank you. I didn't say this at the time because I didn't know if I'd had time, but I called it a slow flow version of the Safman-Taylor finger problem. Now, I expect a lot of you have heard of, if you put a viscous fluid between two parallel plates, glass plates, and you put them on, put the plates vertical on the desk, and you let air come in at the bottom. You can see, and there are walls on the top and bottom, so it's a thin film flow with side walls, just like this, that a bubble of air can, under gravity forces, can penetrate the film and rise through the Healy-Shaw cell. And they did this famous experiment in 1956 where they found that the bubble, no matter how they set it up, always seemed to have the same values of HB and HC, that the bubble filled half the channel. And it was a fantastic subject of research for the next 30 or 40 years as to, because you could then, there was only one complex variable, one potential to be found, and it could, although it's a free boundary problem, Philip Safran was able to solve it by a simple conformal map, and he found that the answer, it said that there was this particular one finger, half the width, but that the solution was not unique, it could go at any speed. And there we were. They had to try and predict this. And so people tried to regularize the problem by putting in surface tension, and sure enough, it turned out the surface tension going to zero limit was a very singular limit. And using exponential asymptotics, there were in fact an infinite number, countably infinite number of solutions for the Safran and Taylor version of this problem, each for in the limit as the surface tension got smaller and smaller. But all those different solutions collapsed onto the Safran-Taylor curve as the surface tension tended to zero. So you had to put surface tension in to get a discrete set of solutions, but the surface tension going to naught limit was very degenerate. And that, I have a feeling, might be the case here. But on that note, I think I'll stop. Thank you for listening to me.
Thank you very much, John. Thank you very much, Hilary, for this very good, nice talk. So we have time for questions, and also Hilary, if you stop sharing your screen.
Well, I depressed stop sharing and it doesn't do it.
Okay. So yeah, it's could take time.
That's okay.
Yeah, but yeah, we're still waiting for your camera. It's not yet.
The camera's on, isn't it?
Yeah, our camera is on, but
it hasn't got a red light on. Oh, dear.
Well, when I said stop sharing, well, I'm glad you're still there anyway. We never know whether you're there or not.
Yeah. No, many people are here, so it's not just me. So okay, so we are waiting for no, Jean-Marc, it's your camera.
Can anybody? I can't do anything. I've got no control of anything.
Jean-Marc, you manage, but Hilary, we need to see Hilary. No, not yet.
Yeah.
Okay. So if any questions from our participants, please. So you can just you can just ask your question. Yeah, Frank, please.
Yeah, very nice talk, John and Hilary. Thank you. Do you imagine that the tongue you were talking about towards the end? Do you imagine that was going to flow on top of the incoming liquid layer?
Yes, didn't I draw that more or less?
Yes, and that's certainly what Tom observes.
Yes,
okay.
If you put powder on the top of the tongue, it flows. The powder moves downwards.
Yeah, I see. Okay, that's interesting. I didn't see that so much in his picture, but perhaps I was looking at the wrong thing.
Well, there was a dividing streamline coming out of the tongue tip.
Well, the picture we had was only for the block, but it does look very similar for the. We didn't do a picture for the. We haven't got.
Well, the block one always has an
picture for the
unsteady
cylinder.
tongue, and the question is, does the cylinder have
Yeah,
a
I
steady tongue? I'm not sure. But sorry, can we go? If we go to the last slide, I thought I drew a dividing streamline for you, Frank. I'm not sure. I hoped I had. There, yeah, on the bottom left there, there's a dividing streamline between the tongue fluid and the incoming fluid up the belt.
But this area here is still thin.
Yes,
It's the other solution. There are two solutions for the thin.
If you write down a free surface parallel-sided thin film, you get a cubic equation for the thickness in terms of.
Hilary, I'm sharing my screen, so I'm showing your slides. So we cannot see.
Well, I don't know how to get rid of them.
Yeah. So I show your slide. Which slide to show? Now I'm showing 19th.
Yes,
okay.
That's right.
Okay. So just tell me which slide to show.
Okay, right. We will tell you.
What shall I do to come back so we can talk to you?
Stop sharing.
I can't stop sharing. I have nothing to press that says stop share.
This is Oxford University Mathematics Department.
Sorry.
It's to do with me not knowing.
Yeah, because I don't know what's happened because
now I've got you. Okay, we're right. We're here now.
Are we?
Yes, we're here.
Good.
And now we can actually reveal ourselves.
Okay, and can anybody see us?
We might be able to if they look.
Yeah, done. Okay, perfect. So
nice.
Then from now on, I can show the slides if needed. Can you see the slides?
Yes.
Yeah. Okay. And also I can make it full screen if needed. Yeah.
Very good.
Mm-hmm.
Could I also ask what the fluid is in?
Oh yeah, it's I can even give you its chemical composition. I think
very sticky silicon oil.
Silicon oil.
Okay.
Where did?
I don't know. But anyway, it's
silicon oil with viscosity of 13341 plus or minus 50 centipascal at 21 degrees C.
Yeah. So pretty viscous and pretty dense.
Yes, and crucially, I think with a low surface tension.
Okay. But John, if it's a high surface tension, or we increase surface tension by surfactant, say, what's happening?
All kinds of things. Okay. Well, for a start, it will become. I think it will become more difficult for the fluid to go around the top of the cylinder. I think it will separate. The surface tension forces will take most of the fluid up the belt, and so you'll get less and less fluid around the cylinder. And then it becomes more like a lot of the problems in lubrication, in ordinary lubrication of bearings, where the cavity goes all the way to one side of the bearing. So that can have quite a strong effect, and there's a lot of literature in that limit when the surface when the capillary number gets to be small.
Right. And what would happen if omega equal to big U? So if the speed of the bell and speed of the cylinder are the same, or it's never happened?
No, it won't happen because the belt is dragging the cylinder.
Yeah.
This cylinder is not being driven. You see, it's being driven by the fluid.
Yeah. So the omega is calculated as the function of U.
Yeah, yes. U is part, and omega is one of the variables we have to determine.
Yeah, and did you show how it depends on, no? How omega omega behave as function of u, no?
We do have all that data. I expect no, might have it to just think of it.
No, I don't think I've got that. No, we certainly haven't put it on there.
I'm sure Radu has it all, but I don't think.
Maybe Mo could.
Mo, can you comment on how omega varies?
Yeah, so essentially omega is bounded, omega over u is bounded above by about 0.7. And you can show that from the calculation.
1.7, is it right?
0.7.
Not 0.7. Okay, so it's always smaller.
Yes, exactly, because the belt drives the rotation.
Okay, but it cannot be the same as the yeah. Okay, and is it possible that omega is just 0?
In the limit of small m, omega tends to 0.
Okay, I see. It's also interesting that you showed the calculation by Radu, and indeed he did his calculation are very powerful. But it's strange that, as you said, that picture in this slide, which is now displayed. I understood that he did not manage to calculate that the case with the flooded region.
No.
No.
We didn't. He hasn't tried that one. He's done the upper end. Yeah.
So okay, but so this means he did not try to solve this problem.
The bottom, the one near x minus, no.
Okay, because that would be interesting, and in particular, you can see there is over here. It seems that there is like a stagnation point.
There's a stagnation point on the free surface. Well, that's that is pure conjecture. That was the case for the block, but whether it happens for the circular cylinder, we don't know.
Yeah. That's
Sasha, I should say this is complete conjecture, this last slide. It is also, if it's correct, it gave this very strange result that the mass of the block must be the 9/4 power of epsilon. But a lot of experimentation would be needed to check that out. This is very much work in progress.
Yeah. But that is kind of for me, it's very reasonable. First of all, but also it gives the idea that because this is what's shown here is the lower part. It's when where the film is just coming to the cylinder,
and out. Yes.
Yeah, and you see, it's making the cylinder making kind of step, and making the film thickness, increasing the film thickness. So this is kind of it's a kind of additional support for the cylinder.
Yes, indeed.
Yeah. Okay.
Yes.
I believe it's right, but then it's something about cylinders or machine who can think about and make something for itself. Adjusting the weight, position on the belt. Yeah, it's very interesting. And
if you think of the block, I would draw a similar picture to this one for the block, except the circle would be 90 degrees.
Yeah. But for blocks, that is the stagnation point, say, locally, local stagnation point is moving, right? As you showed in the photograph.
But there will still be a two-dimensional slow flow region. And, if only we were more confident in the asymptotics, I would be trying to ask Radu to try to do this when he has some time next time around.
Yeah. Yeah. And also with that computations, there are new software appearing like that Basilisk, which could be better in some respects than the J's.
It was, but I think he used Basilisk.
Oh, he used Basilisk. Okay.
No, did he not?
Yes, he used Basilisk.
Okay, so that is the top of modern computations. Yeah. Okay. On that hand, I'm sorry for asking many questions, but I'll ask other participants soon to to share their thoughts. But it was the calculation done by Radu were done for say upper part at the separation point. The potentially he can do also the picture, the case shown over here. This is for lower point where the layer from the top of the cylinder comes to the comes under the cylinder. But I'm just wondering, it's possible actually to calculate everything all together, including the layer on the cylinder. I don't think it's a big problem for Basilisk, is it?
Well, it took Mo. How long did it take Radu to do the X plus region? Quite a few weeks, wasn't it?
So each inner problem, I think took about 4 to 8 hours on his laptop, and then that's for one specific set of parameters. So for each parameter set you want to do for the inner problem, it's about 4 to 8 hours on a laptop.
And I think it's only inner problem.
Yes. Oh. I think the issue would be that you have lots of very thin layers, and resolving those and all of them and all of the coupling would get quite complex quite quickly.
Yeah, indeed. Yeah.
And the geometry in this bottom corner is much more uncertain.
Yeah.
Well, we're not that. It is.
But we don't need it. I mean,
It's if it's possible, it would be helpful to have a CFD results for this problem.
Yeah.
Any other questions, please? Any other? Just switch on your microphone and ask questions. Anything?
Yeah. Hello. Do you hear me?
Yeah.
Yeah. I'm from Vienna, I have also a question regarding this conjecture. Given this conjecture is true, shouldn't there be a cusp type merging of the free streamlines on the top surface rather than a stagnation point? Because you annihilate a free surface. So wouldn't we expect something like the two free surfaces are merging?
For rotating cylinders, right?
Yes.
It's like for rotating cylinders. Okay.
Yeah. Right.
Yes. Well, I think that's a very real possibility, especially if the surface tension is very small.
Yeah.
And that's why I don't dare suggest to Radu that he should go and look at this until I know whether to expect something. There could well be a cusp. Like no reason why not, because cusps very often form if you do put some silicon oil in a jar and turn it upside down, you'll see a cusp in the free boundary. I think it's a very reasonable possibility.
I think so, because you annihilate a free surface, and physically, when you consider the motion of the individual fluid particles, shouldn't we expect that?
Yes, indeed. And indeed, if you like cusps, the guy Richardson, are you familiar with his work?
Yeah, I am. A little bit.
He has studied cusps, hasn't he? Because they develop when the fluid separates from a boundary.
Yes. Yeah.
Something like that could well happen here.
Yeah.
Okay. Thank you very much. Very interesting.
Yeah, very interesting. So any other questions? it's a John, you mentioned that there is a condition at the x plus or x minus, I don't remember, that the pressure is not only zero there, but that the gradient of pressure also zero there, right? And you said you don't like this condition. As I remember. Sorry?
Yes, sorry, go on.
Yeah. But that condition, I believe it's called the Brillouin-Villa condition. It's about the separation, right, or non-viscous separation, right? So then the condition is kind of reasonable, I believe. No.
Well, I'm not quite sure what name the Reynolds condition is that the pressure gradient is zero, which is not bad, but it's not very good. And then there are all these Coyne-Elrod, Taylor conditions, Savage conditions, and now the Scriven and Coyle conditions. So that's all this research has been going on, and I think that the condition has got to come out of the solution of the problem I showed on page 9, and that's got these two results that Radu was able to get numerically.
Yeah, and is this problem relevant to problem of just the stationary plate, horizontal plate, and film on it, and circular cylinder sitting on the film, and the cylinder rotates, and the kind of taking oil, or not oil, but the fluid on it, and returning back. So kind of the same problem, but without gravity, stationary problem, and the no belt motion.
Yeah, that is the absolutely standard textbook problem for lubrication theory.
Okay.
And
but is it,
to solve that problem, you do need two conditions at each end of the lubricated region.
Okay.
And but in that problem, you probably will not, in most situations, get a film going around the cylinder, or if you do, it'll be very thin. I think it is with this silicon oil and the parameter regime that Tom chose is what gives this. But that is an even simpler version of the problem. But that one you can sort of find in textbooks.
Okay. So that is the version, but simplified version of the presented problem.
Yes.
Okay.
May
any other questions, please?
Yeah, I've just a further question concerning the Reynolds condition. As far as I know in lubrication theory, the Reynolds condition is nothing more than you take the Reynolds equation plus conservation of mass. And I think what people do in tribology and so on is to just say, okay, when you have just the Couillette flow further downstream, there's no pressure gradient. So simply take the pressure gradient as zero, and you take the pressure as zero, equal to the cavitation pressure. But there's not much theory behind. I think this is an unsolved problem. It's fully unsolved.
Well, this is what we think that this numerical calculation that Radu did provides us a logical answer to it. It's certainly not a simple relation between P and P prime. It involves relative velocities and thicknesses, and those two pictures I showed you from Radu's calculation, those are the two unknown conditions, and they don't nothing like Reynolds condition.
Right. And I think in the classical situation, you have the film ruptures as a whole from the lower surface where U is zero, and you have omega given. That's the main difference. There's no fingering.
And also, the same thing can happen when the oil film, instead of separates, it could evaporate if you had it in a hot atmosphere.
Yes.
And then you would have a whole new set of conditions then.
Yeah, but you need a wetting property, because you have no wetting properties, because everything is wetted here.
Everything is wetting, yes, but it could evaporate.
Yeah, it could evaporate,
Okay.
Thank you very much. Thank you.
Thank you. Yeah, thank you very much. Thank you very much. Thank you, John. Thank you, Hilary. So I stop sharing. once again, let's thank our speakers for today. Very interesting presentation and exciting presentation. And you can see there are many still problems to solve, and in asymptotic analysis, and even with calculation, or sorry, computations, because the computers are not yet so powerful to solve the problems of interest, and there could be experiments and variation of the properties and other things. So that is a very, very exciting and yeah, the inspiring presentation. So thank you very much. Thank you, Hilary. Thank you, John. And now I stop the recording, and after that I'll still be online. Because I need for the file to be downloaded. And if you need that file, let me know. The university is thinking about to make a channel, a YouTube channel for our seminar. So then we will ask our speakers to give us permission to upload their presentation to the YouTube, and then there will be many people. So thank you very much, and yeah, we are close our seminar. Please remember the next seminar will be on 17th next week, and it will be about viscoelastic properties of ice, modeling, and experiment. Very interesting topic. So the John, I'll send you also the link to that seminar.
Thank you.
Either I sent it already. Yeah. So that is another very interesting topic. Okay. Thank you. Bye bye. So see you next week.
Thank you.
Yeah. I stop recording.